All right, so let's go through this application exercise. In this one, we are calculating confidence intervals, and we're doing it quote-unquote by hand, and then we're doing it using the conf_int function to make sure we did it well. All right, so the first question is to fit a model predicting y from x. And so I've given you this little data table here with y and two predictors, x1 and x2. So first, the easiest one to create is the y. So I'm gonna, let's call this chunk input data. So let's first make our vector y. And so this is 1, 3, 5, 6, 1. And now let's make our design matrix x. So I'm gonna do this in parts. I'm first gonna create a vector for x1, which is gonna be 3, 3, 1, 7, 1. And then I'm gonna make my vector for x2, which is going to be 2, 6, 8, 9, 2. And then I'm going to combine these all into that big design matrix where the first row or the first column is all ones. So we're going to have 5 ones, and then we'll have x1, and then we'll have x2. And we want this to have 3 columns. So let's run all of that. Let's make sure it worked, y and x. And so to fit that model, we know that our beta hat is going to be equal to x transpose x inverse, so x transpose times x, and we use the solve function to take the inverse, times x transpose times y. So that's our beta hat. So let's look at those values. So beta 0, our intercept is negative 0.55. Our beta 1 hat is 0.057, and beta 2 hat is 0.6639. Okay, so when we're calculating the confidence intervals by hand, the first thing we need to do is we need to get the to calculate the variance of beta hat. And so what are the components of the variance of beta hat? Well, there's sigma hat squared, and there's also x transpose x inverse. So we already have x transpose x inverse, and so we just need a sigma hat squared. And so let's remember what the formula for that is. That's going to be the residuals summed up and squared. So the residual sum of squares divided by n minus p plus 1, which in this case is 3 because there are 2 predictors, p, and then 1 for the intercept. So n minus 3. Okay, so maybe we should calculate the residuals first. So the residuals are going to be, maybe we'll just call these b. And that's going to be y minus y hat, which y hat is just equal to x times beta hat. And let's make sure this works. That looks good for x times beta hat, and so y minus x times beta hat is going to be our residual. Okay, so now we've got those residuals, and so we're going to sum the square of residuals, and then we're going to divide by n, which in this case is 5, minus 3, p plus 1. So that's our sigma hat squared. Our variance of beta is going to be that sigma hat squared times x transpose x inverse. So let's look at that. Okay, so I want to talk about what this variance matrix is. This is a variance covariance matrix, and I think we've been using this a lot, but I want to make sure that we explicitly understand what each part of this is. And so you can think of each column as corresponding to each of the beta coefficients, beta 0, beta 1, and beta 2. And you can think of each row as also corresponding to each of those beta coefficients, beta 0, beta 1, and beta 2. And so we know that the variance of so like the variance, for example, of beta 0 is going to be equal to the covariance of beta 0 with itself, right? So if you're taking the covariance, I'm going to just write this in the thing so you can see what I'm talking about. But if I take the covariance of x and x, that's going to be equal to the variance of x. Because this is just by definition. We know that if you're taking the covariance between two things that are the same itself, that's the same as the variance. We proved this early on in the class. Okay, so if you think about these rows and columns, this cell here is the beta 0 row and the beta 0 column. So this is the covariance between beta 0 and itself, which is the same as the variance of beta 0. So this value right here is the variance of the intercept. This is going to be the covariance between beta 0 and beta 1, because if you remember the order, this was beta 0, beta 1, beta 2, and the same on the rows, beta 0, beta 1, beta 2. So this is the covariance between beta 0 and beta 2. So this is the covariance between those beta coefficients. And what do you think this is? This is the covariance between beta 0 and beta 1, or beta 2, rather. So this is beta 0 and beta 2. So this is beta 0 and beta 1. This is beta 0 and beta 2, the covariances. Now look at this matrix and see if you can find those same values somewhere else. And so this is exactly what we would expect, because if this is the covariance between beta 0 and beta 1, and we know that this second row corresponds to beta 1, and we know that this first column corresponds to beta 0, then this is going to be that same value. This is the covariance between beta 1 and beta 0. So we can write this like this. This is the covariance of beta hat 1 and beta hat 0, which is equal to the covariance of beta hat 0 and beta hat 1. So these are both the same. They're both this negative 0.1269, negative 0.1269, exactly as we'd expect. And similarly, this value right here, this is the covariance between beta 0 and beta 2, which is exactly the same as the covariance between beta 0 and beta 2 as put right here. And so this is going to be the covariance between beta 1 and itself, beta 1, so that's the variance of beta 1. And this is going to be the variance of beta 2. And so that's why when we're trying to get the standard error of these beta coefficients, we first take the diagonal of this matrix. We take the diagonal of this matrix and we end up with just the numbers that are on the diagonal. So just the variance components, the 0.21, 0.1269, and 0.007. So we're just taking the diagonal here. And that's basically because we're not interested really in these covariance values, the covariance between each of these beta coefficients. We're just interested in their variance because we want to be able to take the square root of that to be able to construct confidence intervals. So if I want the standard error of the beta coefficients, I'm going to take the square root of the diagonal of that variance, covariance matrix. And so now I end up with these standard errors. The standard error of beta 0 is 0.46, the standard error of beta 1 is 0.11, and the standard error of beta 2 is 0.083. Okay, so what do we need to be able to construct a confidence interval? Well, a confidence interval for the lower bound is going to be equal, maybe I should call it lower bound of beta. This is going to be equal to beta hat minus t star times the standard error of beta. Now, we haven't figured out what this t star is, so I'm going to do this here in this line. Let's name this chunk, by the way. Let's call this CI for confidence interval. Okay, so now how do we get this critical value for t? Well, as I mentioned, there's this qt function. I'm just going to pull this over here so we can see what this does. But this qt function, so the student t distribution, and this is the qt is the quantile function for the t distribution. And if we look at how this works, we need to give it a value p, which is a probability of interest, and we need to give it a degree of freedom, which in this case is going to be n minus p plus 1. So let's use that qt function. And what are we going to put in for p? Well, we want to calculate a 95% confidence interval. And so we're going to put in 0.975. And the reason we're putting in 975 instead of just 95 is because this is a two-sided interval, and we want to make sure that we have 5% total on either side, total between the two sides, which is going to be 2.5% on either side of the distribution. So we're going to do qt 0.975. Degrees of freedom is 5 minus 3. So that's the lower bound. And then the upper bound of beta is going to be the same thing, except now we're going to add t star times the standard error of beta. Okay, so now let's take a look at those. Let's look at that lower bound. And actually a trick here is if you want to both assign something and look at it when you output, when you run a chunk, you can use these parentheses and it'll print the output. So this is the output here. Our lower bound, we've got negative 2.5, negative 0.42, and 0.3. And our upper bound, we've got 1.4, 0.5, and 1. Okay, so we've done it by hand. And now the next question is to check this answer with the compint function. So let's run compint, and I'm going to do this on lm y tilde x2 plus x3. And so what I'm doing here is I'm just taking and in fact, instead of that, I could, if I wanted to, do this, y, x1, x2, because I created these vectors for each of those. So I'm going to do that instead. All right, so let's check these answers. Well, you can easily see the upper bound here, so let's look at that first. The upper bound, we've got, for the intercept, 1.43, exactly the same. For the beta 1, we've got 0.54, there it is, exactly the same. And same for the upper bound of the of beta 2, 1.02, 1.02. So now let's try to remember these. We've got negative 2.5, negative 0.4, and 0.3. And there we have negative 2.5, negative 0.4, and 0.3. And so we got the same exact answer. And so it looks like our by hand calculation worked. Good job. Okay, so now this is the tricky part. We need to interpret these intervals. And so this is so crucial and so important because I think that this is somewhere where in statistical inference we get really tripped up. But what this means is if we were to repeat the sampling process that got us our data, which is our y, x1, and x2, many times we'd expect the true value for the beta coefficients to fall within the intervals calculated 95% of the time. Now, I've highlighted intervals here because what I mean by this is we are not saying that, for example, beta 1, the true beta 1 is between negative 0.4 and 0.5. That is not true. It's not between those values 95% of the time. If you remember from that app we created, this is just one of the many intervals that could be calculated. And what we're saying is we expect that beta coefficient, the true coefficient, to fall within the confidence interval that's calculated, the confidence intervals that are calculated 95% of the time. So each time we're going to get a slightly different confidence interval, but we'd expect that 95% of these intervals would contain the truth. So the confidence intervals really tell you something about the sampling process. Okay, so now this last one was a bit of a stretch goal. It asked you to calculate the joint confidence interval for beta 1 and beta 2. So this one was kind of hard, but if you looked in the book, it gave you some insight into how you can actually do this. And so there's a package. You can do it by hand by using some theory behind basically how ellipses work. As I mentioned in the lecture, we expect that this confidence interval is going to be an ellipse, and we can use some inequalities that include an F distribution to be able to sort of determine which values are inside and outside that ellipse. But if you read your book chapter, you would see that there is a package called Ellipse that will actually calculate these for you. And so you're going to use that, you use the ellipse function, and you set the model. So I'm going to fit this model again. So I'm doing lm y x1 plus x2. So that's my model. And you plug that model into the ellipse, and you tell it which values you'd like it to look at. Well, let's just see what happens if we just run it like this. So if we just run it by default, it's going to tell you the joint confidence interval between the intercept and x1, which was not what we wanted. We want the joint confidence interval between beta 1 and beta 2, and so that's going to be between x2 and x3. And so if you check out that ellipse function, oops, the ellipse function's help file, you'll see that there is a which argument, and the which argument says which pair of variables should be used. And so I'm going to say which equals, and I would like for it to use the second and third instead of the first and second. The default is the first and second, so that would be, if you were looking at a beta matrix, that would be beta 0 and beta 1, but I wanted to use beta 1 and beta 2, which is going to be 2 and 3. So let's try that, and now we've got x1 and x2. And so this, by default, it will give you 100 points to use in this ellipse. It's going to generate 100 of these. And so this is going to be my joint confidence interval. And so now let's go ahead and plot this thing just to see what it looks like. So there is my joint confidence interval between x1 and x2. So that looks pretty good. That's a nice little confidence interval between these points. If I thought that, you know, this looks pretty precise. I mean, you can tell exactly what this picture is trying to get at. If I wanted to have more points, I can just change my endpoint. So I could up this to maybe 200. And that's just going to give us 200 points, so a little bit tighter. But again, the 100 default seems to be just fine. All right, now if I wanted to, let's say I wanted to put this into basically a plot that also included the values that we calculated for the lower bound and the upper bound. And so what I'm going to do is I'm actually going to turn this into, I'm going to use ggplot instead. And so this joint CI object, this is a matrix, and I want to actually use this as a data frame because I'd like to be able to plot these values as a data frame. And so I'm going to just change this to as data frame. So I'm going to call this joint CI data frame. I'm just going to do as.data frame joint CI. Let's take a look at that. So it looks exactly the same, except now we've got this in data frame form, so we've got x1 and x2 are my two columns. So now I can do ggplot, joint CI data frame. My aesthetics that I'm mapping to on the x-axis, I want to map, I'm going to make a point for x1. On the y-axis, I'm going to have a point for x2. And since this is points, I'm going to use geom_point. And so all of this that I'm showing you right now, this is all superfluous. You didn't need to do any of this for this, but I just think it's helpful to sort of see how I would work through some of these problems in case you're interested in taking things a step further. Oh, goodness, I have to load the ggplot package, so let's do that. Library ggplot2. Okay. So now let's see what this looks like. All right, so it looks exactly like it looked in the plot that we made before. And actually, instead of using geom_point, I could swap this out for geom_line. And oh, that looks crazy. That wasn't exactly what I wanted to do. I wanted to connect the dots. So we're going to go back to geom_point because otherwise we have to kind of sort this so that it does it in the right order. So let's go back to geom_point. Okay, so let's put the points. And now what I want to do is I would like to plot basically a vertical line at where the confidence interval for the lower bound and the upper bound of x1 are, and I want a horizontal line for where the lower bound and upper bound of x2 are. So I can use this geom_v line will create a vertical line, and I can set the x-intercept for this vertical line, and I want it to be at the lower bound and upper bound for x1. And so let's remind ourselves where the lower bound are. So this is my lower bound object. And so I'm going to do, I want to pull for x1, that's going to be the second element of this lower bound object. So LB beta 2. Let's just look at what that is. If I just run that part, it's going to be 0.42, which is exactly that point that I want. And then I would like to also plot the upper bound of beta. So we want the upper bound. So that's going to add, and let's make these dashed so the LTY equals 2. Okay, so that creates the bound for x1. And now let's do the same for GMH line, x, y-intercept. So now I'm setting the y-intercept for x2 here. And so for that, I'm going to do LB beta 3 and UB beta 3. And let's make those dashed as well. Okay, so here, this shows what we get when we use just the univariate or the confidence interval just for the individual points. And so you can see that the ellipse, they all are sort of centered. The points here where the confidence intervals are centered is at their coefficients. And so the coefficients, if we look at beta hat, the coefficient for x1 is 0.05. And so it's like right around here, which is exactly the center both of the ellipse and of our dashed line. And the coefficient for beta 2, beta hat 2 is 0.66, which is right around here, which again is right in the center of both our ellipse and our confidence intervals. And so the centers agree, but the actual area contained by both, they disagree in pretty big ways. And so if we're actually interested in like the joint confidence interval, it can be really important to actually use this theory to be able to calculate that appropriately. If you're interested in the confidence intervals across two different coefficients, you want to be incorporating that information appropriately.